In this problem, we're asked to find the time domain expression for each phasor below. The time domain form is assumed to be similar, and then we are given this equation right here. And this is how we're going to write it for all of our answers for A, B, and C. To start this off, we are going to look at A. Well, we are given the Vmax right here, and then we are given the phase angle right here. We don't have to add it to anything, so this is actually just our answer. It's going to be 18.6 and negative 54, because again, we are given our Vmax and our angle, and there's nothing to change or add. For part B though, it's a little bit more complicated. Instead of just plugging these in, we have to add these together. However, we can't just add 50 to 20 and 45 to 30. Instead, we actually have to change this to the, I think it's called rectangular form. And basically what we're going to do is call this our I1 and this our I2. So I'm going to write out our I1, and after we do this, we are going to get this for both of our equations added together. Now we have to convert our added value back into this form so we can put it into this equation. An important note that confused me a little bit is that this negative sign is not like outside of the parenthesis. It's not going to be a negative 50 and then a positive 30 degrees. It's just going to be negative 50, and this remains unchanged at negative 30 degrees as well. So for this, first thing we need to do is find our Vmax. And to do this, we are going to have the square root over our real number, which is negative 29, and then our real number is going to be squared, plus our imaginary number, which is 39, and this is also squared. And this is going to give us approximately 48.6, or that our V of m is equal to approximately 49. So we're going to remember that for part of our answer. Now we are going to solve for our theta, and this is going to be our angle for the phase shift, and it's equal to a tangent negative 1. And then inside of here, we're going to have our imaginary number, which is 39, over our real number, which is negative 29. And then we can plug this into a calculator. And from this, we are going to get that our theta is equal to negative 53.4 approximately. However, this is not our actual theta. If we look back at this part right here, and we actually graph it, so we'll draw a graph like this, we have our negative 29 as our x. So this is going to be basically our x-axis, and this is our imaginary axis. And so the negative 29 is going to be on this side of our axis, because that's the negative. Then our positive is going to be on this side of the axis, because it's our positive. So we are going to have something that looks like this. Now our negative 53.4 is an angle. So if it's negative, it's going to be going this way. So our theta line is going to be like this. However, we can see that it's actually on the opposite side of our equation, which is not right. So what we need to do is add 180 to this. And if we do that, we will be able to get the correct theta. So with our incorrect theta that we have, this 53.4, we are going to add 180 degrees. And from this, we are going to get approximately 127 degrees. So this is our correct theta, or the correct phase angle. So now we can plug this into our formula. We're going to have a 127 here, and then our Vmax is 49 here. And that's the reason why it's 127, not negative 53.4. Now we're going to look at part C. In part C, we already have one part that's in the rectangular form. Again, I think that's what it's called. I'm not 100% sure, but that is in our rectangular form. And I think this is our phase form. I might have those two mixed up, but basically they're in different forms. And this is the form that we want to get this to, so that we can add them together. So all we need to do is convert this second part right here. To do this, it's in volts, so we'll have our V, and then inside of here our negative 30, angle 15 degrees. Remember that the negative only inflicts on the 30 and not the 15 degrees. From here we're going to have our Vmax outside, and then inside of here we're going to have our cosine with our angle, plus the j times the sine with our angle. And if we do this, we are going to get that we have approximately negative 29 plus a j times a negative 7.8. Now we can add this to this value right here, our 20, and then our j80. If we do that, we're going to get approximately negative 9 plus j times 72.2. and this is going to be our equation. Now we need to find the Vmax for it. So again, we're going to do our Vm is equal to the square root of our real number, which is -9 squared, plus our imaginary number, which is 72.2 squared. From this, we're going to get that our V of m is approximately 73. Now we need to look for our theta, and this is going to be equal to the tangent of our -1, and then inside of here, we are going to have our imaginary number, 72.2, divided by our real number, -9. And from this, we are going to get that our theta is approximately -83 degrees. Now we need to check this again. So if we plug this equation right here into a graph, remember our x-axis and then our imaginary axis, because our x is this first part and x always is written first, or normally it's written first. So we're going to have a negative. That means it's going to be on this side. Our imaginary number is a positive, so it's going to be on this side. That means we're going to have something in this quadrant. The quadrants are the important part, not actually where the direction is. Now, if we plug in our negative angle, it's going to be a -83 degrees, and we can see that again, it is on the opposite side. So to get it in the same quadrant, we're going to add 180 degrees. So for our -83 degrees, we're going to add a positive 180, and we're going to get approximately that our theta is equal to 97 degrees. And then if we plug this into our answer, we can see that we get 97 degrees here, and we get our 73 Vm here. And that's how you would go about doing this problem. If you want more introduction to circuit analysis or phasors, there is a playlist and notes below the like button in the description. Previously in another problem that we did, the actual very last problem, we did these and we didn't graph or check them, which I mean is okay, and that's only because these answers worked out. However, we should, and I'm only saying this just to emphasize this part, this graphing part. This is to make sure that our actual angle is on the correct side, because when we do the tangent of -1, sometimes it messes up and we have to have, it doesn't mess up necessarily, but sometimes we need to add 180 degrees to this. But if we look at these, we can see that we did these all correctly by chance, and that is because if we graph this, we know that we have a positive x, so it's going to be on this side, and a negative imaginary number, which will be right here. So our graph's going to have something like this, and we have a negative angle right here, so our angle is going to be in this quadrant as well. If we do something like this for b, we have a positive x, positive imaginary number, so it's going to be in here. Our angle is positive, so our angle is also in here, so that is good. With c now, when we look at this, positive and positive, so it's going to be in our first quadrant. We have a positive angle, so first quadrant again. When we look at D, we'll graph this. We have 0, 0, and so our angle is 0. That makes sense because our angle is going to be like this, and obviously our equation is going to be like this as well. So it's super important to graph these and actually make sure that the angle is correct.